Hi students, so let us try to plot the Bode plot for this particular transfer function. Uh, Here we have a constant term of 10 and we have a pole at the origin, and there is a pole at minus 10, there is a pole at minus 50. So this is the location of poles, and of course there are no zeros. This is a pole at origin, so there is a pole at minus 10 and there is a pole at I think this is minus 50. So 1 over 0.02 is, so this is 0.02, 1 over is 50. So these are the pole positions. We are asked to find, we are asked to plot the Bode plot. So we will maybe in the coming videos we'll see, okay, how do we find the stability of this system using Bode plot. So for the time being, so let us try to understand how do we plot the magnitude plot for this particular open loop transfer function with negative feedback, and this is negative feedback. We are assuming HFS is equal to 1. So what we'll do is, so we will not go by individual terms, so but we'll go by the this slope table and the magnitude at the origin concept what we discussed in the previous example. Okay, previous example is this. So we started with this example and we wrote magnitude at the origin where you have only 10 is contributing at 0.1 radian per second. Of course, this is the magnitude what we thought, because these two are not contributing anything. So that's why the term that is contributing is only this. So, and of course, we wrote the slope table and then we could able to plot the overall response. So we will do the similar type of analysis for this particular transfer function where it has got a pole at the origin and two poles at minus 10 and minus 50. So to start with, I need to know what is magnitude at the origin. So when I say origin, the starting frequency of the Bode plot on your semi-log sheet, if you assume the starting frequency as 0.1 radian per second, so which we'll discuss in the coming videos why we are taking it as 0.1, so why not 10, 100, so on. So let us start with a low frequency of 0.1 radian per second. So at 0.1 radian per second, the terms that are contributing are, if you see each one of these terms, so we know that the magnitude contributed by this is independent of frequency. So this term 10 will going to contribute at each and every frequency. That contribution is, in terms of dB, it is 20 log of 10. 20 log of 10 is the contribution of this term. Coming to this 1 over S term, so as we saw in one of the videos which we discussed last time, so do we know when we actually discuss the frequency response of 1 over S term, so this contribution, you can see at 0.1 radian per second, it is contributing something. So its contribution is not 0 dB at any point of time except at omega is equal to 1 radian per second. But at different frequencies, it has got its own contributions. So now we need to know what is the contribution of this 1 over S term at omega is equal to, so this term 1 over S term at omega is equal to 0.1. So it will be minus 20 log of omega. So now why this I am writing this as minus 20 log of omega, because I know that, so the term what I am looking at is 1 over S. So I know that this 1 over S term will have a plot something like this. So this is the plot what you have. So is this your plot? So this is 0 dB at 1 radian per second. So you are looking at 0.1 radian per second. I know that this slope is minus 20 dB per decade. So at 1 radian per second, if it is 0 dB, so when you're going 10, when you're going this by 10 times less, so this is 1, this is 0.1, is the magnitude increased by 20 dB from 0, will it not go to 20 dB? So magnitude of 1 over S term at omega is equal to 0.1 is 20 dB. So that you can get it from here. Suppose if I substitute this omega as 0.1, so what you will get? Will you not get this as minus of minus 20? So does it mean that you will actually get plus 20 dB, whatever that is contributed by this. So this is giving 20 dB, and how much is this? 20 log of 10 is another 20. So is it not 20 minus of minus 20, is it not 40 dB? So what we are saying is this particular transfer function at omega is equal to 0.1, the contribution is by this term, that is 10, and the term which is 1 over s. So contribution by 10 is 20 dB. The contribution of 1 over s term at omega is equal to 0.1 is minus 20. Since it is minus of minus, it is, of course, this is actually equal to, this is contributing 20 dB, so that's why it is minus of minus 20. Suppose if I do this, see now, it is 20 log of 10 minus of 20 log of 0.1. Can you see, are you getting 40 dB? So this is 40. So that's why this is 40 now. So this is MAO at the. So let us now write slope table. Slope. While writing slope table, I have to concentrate on these parameters: terms, cutoff frequency, individual slope, and resultant slope. So let me start with the term. These are the terms, and I have their individual cutoff frequency. Cutoff frequency. There is nothing like individual. The cutoff frequency of this term, and slope. Slope of individual term, and this is a resultant slope. So now what is the first term? The first term is 10 by s. So 10 by s will not have a cutoff frequency, because as we saw here, so this is keep going like this with minus 20 per decade. So cutoff frequency is defined as 1 where you have a change in slope. Suppose if it happens like this, if it happens like this, if it goes like this, then there is a cutoff frequency possible. So these are the cutoff frequencies. But for this, it is something like this. It is going from the initial value itself, it is having a slope. So these type of terms, which is 1 over s or s, will not have any cutoff frequency. They won't have any cutoff frequencies. So cutoff frequency is not applicable, but they have a slope of minus 20 dB per decade. So this is minus 20. So what is the resultant? Resultant is also minus 20, because you don't have any slope before this. Next term is 1 over 1 plus 0.1. Yes, its cutoff frequency is 1 over 0.1, which is 10 radian per second. So its slope after 10 radian per second is again minus 20. The resultant is the addition of the previous resultant slope and the present resultant slope, that is minus 40 dB. So it's like minus of 20 plus of minus of 20. So this is minus 20 plus of this, so it is minus 40. So next term is this, that is 1 over 1 plus 0.02. Yes, it is now 1 over 0.2 is this one. So this is having a cutoff frequency of 50 radian per second. This will also have a slope of minus 20 dB per decade after 50 radian per second. So resultant is minus of 40 plus of minus of 20. This is now minus 60. So minus 60. This is dB per decade. dB per decade. This is again dB per decade. So what does this entire thing says now is the resultant magnitude plot will have an initial magnitude of 40 dB at omega is equal to 0.1 radian per second. Initially itself it will have a slope of minus 20 dB till 10 radian per second. At 10 the slope changes to minus 40. At 50 it again changes to minus 60 dB per decade. So let us see how it looks. So now let me draw this as my 0.1. This is 1, this is 10, let us say this is 100, I have 50 somewhere here, let us assume. So let me assume that this is somewhere, so this is 0 dB, assume that this is 20, this is 40, this is some minus 20, this is minus 40, let us assume. See now, at 0.1 radian per second, what is the magnitude? That's what is magnitude of this is 40 dB. So let me just take this point. This is my 40 dB. This is in dBs. So then it has a slope of 20 dB per decade. How to know that 20 dB per decade? Come down by 20 dB, go by 1 decade. So now you join this line and this line till where? Till the first cutoff frequency comes. So okay, let us assume that the first cutoff frequency is at 10. So it just goes, okay, let me just put this as 20. Let me just put at this as my point. So now this line goes with a slope of minus 20 dB per decade up to 10. So this is minus 20 dB per decade is my slope. So what did I do? Came down by 20 dB, gone by. So let us just take this as 20, this as 0, this as minus 20, minus 40, minus 60. So I came down by 20 dB, gone by 1 decade. This is my reference point. Join this line. This is 20 dB per decade till up to 10 dB per second. So after 10 radian per second, what is the slope? Here, after 10 radian per second, the slope is minus 40 dB. So what I'll do? I'll come down by 40 dB. So this is 0. 0 means I have to come down by 40 dB means this is minus 40. Go by 1 decade. So 1 decade is assume that it is 1 decade is here. So okay, 1 decade is actually 100 now. Here, this one. So now I have to draw a line. So actually what happens is this will have a slope much more steeper one. This is not correct. It will be, of course, when we actually draw it on the graph sheet, it will be, so it will be like this. So it goes like this and then it's come like this and then it will come like this. So this is at 10, this is at 50, this is at 50. Now this you took it up to 100, but at 50 the slope changes. So this you cannot continue. So at 50 the slope, this is from 10 to 50, it is minus 40 dB per decade. You came down by 40 dB, gone to 1 decade and then drawn the line, but you found that this cutoff frequency is at 50 radian per second, it's not at 100. So you stop it at this point. Now what is the slope after 50 radian per second? If you see here, it is minus 60 dB per decade. So now what you do? From here, come down by 60 dB, go by 1 decade. So what is 1 decade of, from here you come down by 60 dB down, go by 1 decade. So 1 decade of 50 is 500. You join this line and this line, it goes like this. So what is the slope of this? Minus 60 dB per decade. You started with 40 dB, magnitude at the origin, came down by 20 dB, gone by 1 decade. That is the slope for minus 20 per decade. This line will continue up to next cutoff frequency, which is at 10. So at 10, the slope changes to minus 40 dB per decade. So you come down by 40 dB, go by 1 decade, take the reference, extend this line till the next cutoff frequency, which is 50. So at 50, the slope again changes to minus 60 dB per decade. So you come down by 60 dB, go by 1 decade, you draw the line till the end. So this is my magnitude plot. This is my magnitude plot. So how about the phase equation? Phase equation, you can write it here. The phase equation, the contribution of this is nothing. So phase, you can write it as contribution of 1 over s is minus 90 degree. Contribution of this is minus tan inverse of 0.1 omega. Contribution of this is minus tan inverse of 0.02 omega. Then give different values of omega starting from 0, go up to infinity. So what you do? Omega and phi. So omega 0 is initial value, infinite is the final value. Even when omega is 0, do you have it as minus 90 degree? These two are not contributing, but this is minus 90. When omega is infinity, this is also giving 90, this is also giving 90. Since all are minus, 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 this is minus 270 degree. So now this varies from minus 90 to minus 270 for different values of omega that you need to find. By substituting the value of omega for the corresponding value of omega that you want to have. So you will get the phase plot also. So we'll see in next problem how do we actually find the stability of a system once we have magnitude plot and the phase values.